So, hey to Dmitry. Congratulations. I'm Madison. I'm on the Kaggle team. Obviously you are some of our top scientists across everything that we do. So well done. It's great to see you again. We're excited to Brian. We're excited to hear more about your. So what I'm going to do is hand it over to I guess Peter. I'll let you give a quick introduction on the other side of the Google house. And then Brian or Greg, I'll let one of you choose German who would prefer to introduce your team. And then once we do your introductions, we'll get off. Tom and Dmitry, I'm not sure which of you may be sharing your screen for the presentation, but we will just let you kind of share your screen, walk through your presentation. The folks may ask some questions about your solution, and then we'll wrap things up. So a lot of info there. Peter, you want to give you, and I guess since Bertrand's coming a little bit late, maybe introduce him even though he's not here.
Sure. So I'm Peter. I work in Google Brain team, and we are the guys behind the GRF environment. As you noticed, like it was open sourced a while back, and we were hoping to push reinforcement learning state-of-the-art research with this environment. There are like different types of research directions that this environment is useful for, specifically like model-based and multi-agent. And with Kaggle competition, we're hoping to get more attention and drive researchers research topics in this direction, and also see what are the pinpoints and what could be improved, what are the issues maybe that we could address over time, what people dislike about it. So happy to hear any thoughts on those topics from you.
All right, thanks, Peter. Brian or Greg, one of you want to introduce the rest of your team?
You go for it, Brian.
Okay. Hey everyone. It's great to meet you guys. And thank you very much for kind of taking part in the Kaggle competition. We were kind of really excited about being able to run this, and the engagement from everyone was brilliant in terms of the number of teams that competed, and kind of fantastic work by you guys to kind of get right towards those top spots, which is fantastic. Just as a way of a little introduction, my name is Brian. So I lead the data insights and decision technology team at City Football Group. This is a team that works across all of our clubs across the world in the various kind of competitions, trying to support and enable them to kind of make better decisions around football performance, human performance, which is your sports science and medical side of things, as well as talent management. So that's the identification, recruitment, development, and kind of realization of their talent. The kind of our team in general is a fairly small team. We try and keep it so we're actually what we are enablers for others, and we educate others to enable them to have kind of the data science skills to ask and answer questions of their data, right? Rather than having a massive data science team, actually having the experts in their field having a better understanding of data. Now, specifically this area for us of kind of reinforcement learning around kind of AI and simulation is really exciting, primarily with the end goal of enabling coaches to kind of test, refine their kind of tactics, whether that's pre-game starting lineups, whether that's match strategies, whether that's in-game decision making, being able to kind of test and refine those and learn from their ideas before the game's even been played, right? So this is where kind of a simulator such as this that you've been working on, it is really exciting for us to, not necessarily as it is now, but what it could evolve into, right? And being able to work with the fantastic guys at Google and Kaggle and have all the great entrants, as well as kind of making us become extremely, even more humble in terms of seeing the quality of some of the people out there. It's exciting to know where that actually this has a future, right? This has legs where we could actually start to really understand football at kind of a deeper level than ever has been before, and give our coaches that power to test and refine and to learn. So I'll pause there and I'll pass over to Greg now.
Well, I think you've introduced from our side very well, Brian. I'll just add, so just so that you know who Ray and I are, Tom. So we work on the technology side of the business, complementing Brian's work on the sort of data and decision side. I'm the CTO, and Ray leads our IT development and data engineering teams. Very, very pleased to meet you.
All right. Well, Tom and Dmitry, I'll hand it over to you. Two of our, and for those of you on the non-Kaggle side, in case you didn't know, they are two of our top grandmasters in general. Dmitry, I think where are you right now? You're still top 10, I believe, overall.
Yeah. As of today, I'm still top 10, but who knows what's going to happen tomorrow?
Yeah. We'll see. So I'll hand it off to you, and we're looking forward to see what you have in store.
Yeah, go ahead, Dmitry.
Yeah, I'll start. Thank you, everyone. It's a pleasure to meet you, and it was a pleasure to participate in the contest. I'll start with a few words about myself. I have a background in data mining and actually quite a few years of experience in financial area back in the days. But a few years ago, I moved to a more general data science area. I'm participating in Kaggle a lot, especially sports-related competitions. There were two really good ones, the Google Research Football, of course, and the NFL competition about a year ago. And right now I work for H2AI, which is an AI-based company from California, basically. Tom?
Right, so I am the chief data scientist at a Norwegian startup, Intellisy, and we try to automate machine learning for industrial customers. I have a background in computer science and statistics. I actually did my master thesis on proposing to change the FIFA ranking, and then 6 months later, they changed the FIFA ranking to the current system. So yeah, big fan of football as well. Before moving to Norway, I was a research engineer at DeepMind, doing research into core reinforcement learning. And I'm currently on the job market, so feel free to follow up after the call. Yeah, I'm going to take you through the reinforcement learning part of our approach. So in summary, what we ended up with is an alpha star type of setup. We will get to the details later on, of course. With the crucial distinction that we had limited resources. And we were asked to summarize the most important elements, and the answer is everything. Like, since this is reinforcement learning, it's incredibly hard to get it right. You need every component to work, and as soon as you get one of them slightly wrong, it just doesn't work. But if you get all of them right, it's like magic. You have a self-improving system, and you can just sit back and see greatness happen. So everything is critical. Getting the environment right, the network architecture, the reward, the loss function, the data that you feed it, the optimization, everything is critical. And to give you an idea, an agent takes about 1 to 3 days on a modest architecture. And then an agent gets added to the pool, and we iterate on that. So it's a reinforcement learning challenge, as stated before. And reinforcement learning is essentially trial and error. And the key problem, I think it's the key problem in reinforcement learning, is to solve the exploration problem. Somehow you have to learn a policy, a mapping from the current state to actions, which does something useful. And since the search space is so massive, there are different approaches you can follow. And what the first and second place teams did was to use massive computational resources combined with handcrafted rewards to guide the search in policy space. We didn't have massive computational resources, so we had to do something else. And one thing which came up before in the introductions was to use model-based RL. So there the idea is that you learn a model of the environment, and then you plan through this learned model to select actions. The issue here is that you play against an opponent, and you don't know how the opponent plays. So it's very hard to factor that into your learned model. The other thing you can do is to use offline reinforcement learning. Why would you do that? Because, as we said, interaction with the environment, that's the actual bottleneck. This is just using trial and error, essentially. So it's very expensive to iterate in this trial and error setup. Whereas in the offline RL setup, the agent doesn't interact with the environment. It just collects data from an agent or a set of agents which interact with the world, and then the learning happens completely offline. And that allows you to be much more data efficient without having this bottleneck. Now, what we ended up doing is somewhere in between. So we started from a clone, and we used off-policy reinforcement learning, which is somewhere in between. And to those in the field, it sounds a lot like the StarCraft 2 approach, AlphaStar by DeepMind. And a lot of what we did is very close to this approach, actually. So in reinforcement learning, as I said, is what you want to do is to learn a mapping from the state to some probability distribution over the possible actions. And you do so to maximize the reward, to make the best possible agent. And what we did is a two-phased approach. So first we use supervised learning to get a sensible starting point. And then we use reinforcement learning to fine-tune the policy. So in the first phase, this is the most straightforward phase. We are trying to take one of the top agents and start from something close to what their policy is. So you can use supervised learning for that. So what we did is we used the Kaggle API to collect state action pairs. So we could see what action was selected by the agent in each of those states. And we just use supervised learning to minimize the loss. And you end up with a policy which is pretty close to what that target submission is doing. One thing which is interesting to mention here is that we use transfer learning to improve this process. So instead of learning your supervised policy for one agent, we did it for tens of agents, where we added this one-hot encoding of the agent ID so that it's uniquely identifiable. And we used supervised learning on all of these submissions. And then we only kept the torso of the network architecture. So the thinking here is that you learn a torso which learns features which are generally useful. And then when you do the cloning on a new submission, you start from a torso which is already pretty smart. It learns generally useful features, and it improves the data efficiency, well, the efficiency of the learning. But crucially, it also improves the performance of the cloned agent. Then next, we use reinforcement learning to improve this learned policy. And to that extent, we made our own handcrafted RL framework, which is inspired by Impala, which was also used in the paper, actually, about this environment. So in Impala, you have an asynchronous setup where the actors and learners do their own thing asynchronously, and they communicate through disk and through a shared memory. So the actors, they take the current network, and they use that to generate data. They interact with the environment, and they store it to a shared replay buffer. And the learner consumes data from this replay buffer to improve the policy. And unlike the vanilla A2C approach, this is asynchronous, so it's a more efficient use of the resources. Now, I've said this a couple of times before. So you have an agent, you have a policy, and you want to improve this policy. And you do so by generating data and then doing more of what worked and less of what didn't work. And the distribution of data in our acting we ended up with was to do 50% self-play and 50% play against fixed opponents. So in self-play, you have the agent play against a copy of itself. And this has some very nice properties. You always play against an opponent of the same strength. It's twice as data efficient because you get to use data from both perspectives. and it allows you to detect flaws in the current policy. The downside is that it can cycle. You can have something like rock, paper, scissors, where you think you're improving, but you're actually cycling. And that's where the fixed opponents pool comes in. So here we sample from a pool of fixed opponents. And these can be clones that we generate ourselves. They can be earlier versions of this agent. They can be public posted agents. And that way we learn to be robust against all these strategies. It's not as advanced as the league training of StarCraft, but again, that's because of limited resources. And we also considered a third mode of data, which was to use data from the games actually played on the leaderboard. And we think this is promising. We didn't explore it extensively, but if you ever decide to run a next competition, this is where we start. Now, the reward is what you optimize for. And early on, we used Monte Carlo RL, which means you wait until the terminal state to assign credit to the actions you took. And the only way you can really do this is to use a handcrafted reward, because there are thousands of steps, potentially, up to 1,500, before something happens, which is an inherent environment reward, like scoring or the end of a half. So what we did is we instead chopped the data into smaller episodes, and then we used the handcrafted reward function to compute how good each state is. Let's say you have the ball, that's probably good. Moving forward, that's probably good. And then some positional rewards. So we spent a lot of effort into this and then ended up not using it because it didn't really work. It's very hard to come up with a reward function which factors in everything that's relevant for the current state. So instead, what we did was to use temporal difference learning, where we used the best proxy you can come up with for winning, which is scoring. And we said scoring a goal, that's good, conceding, that's bad, ending a half, that's sort of neutral. And then we turned this reward handcrafting process into a learning task itself. So now the agent learns the value of each state, and you use that learned estimate to update your policy. And once we switched to TD learning, that's when the magic happened and we saw our agents finally improve. So in terms of the learning, we have 4 losses for the policy, 1 loss for the value function. We can talk more about it in detail, but it are the losses from AlphaStar combined with an additional policy loss to reduce the update size within learning iterations. We use a separate actor and critic network, separate optimizers, and a replay buffer size of 800,000 transitions. Now, what came in really handy during the learning was to look at videos like this. So here you see our agent playing against a copy of itself. On the top left, you see the evolution of the policy for each state. And this is the learning iteration. So you can see that the policy changes over time, and this can give you insights into how stable the learning is. And it helped us stabilize this whole process. Here you see the evolution of the value function as learning progresses, and also the evolution of the value function as the game progresses. These can be quite insightful to reason about what the agent knows and what the agent is doing and why it's doing it. Like here, for example, you see that we are the red agent. Well, we are both, but here on the policy side, that's the red agent. And the opponent is breaking through. So it's about to run to the opponent, to our goal. So here you see the opponent is going to the left. It's sprinting. We are behind. So the agent has learned that it has to do with sliding. It selects the sliding action with 98% probability. And you can see that its value function is now at minus 0.25. And on the next step, there's a free kick, which means that the sliding was successful. And the value function for the left agent goes up, for the right agent goes down. So that means that the environment is stochastic in terms of if the sliding is successful or not. And the agent gets a positive surprise here to see that the sliding was successful. We had some other important and interesting findings on the RL front. So policy gradients are the way to go. We had the insight that the ongoing KL constraint is critical to stabilize learning. We used the wrong environment version for way too long, until 2 weeks before the deadline. And yeah, one final thought is that we tried very hard to get hierarchical RL to work, but nothing was better than our best single agent. Now Dmitry is going to enlighten you about the network architecture.
You can probably continue showing slides if you don't mind. Yeah, thank you. Now a little bit about the architecture of the model we used. We used obviously the neural network here, and the architecture was kind of inspired by the neural network, which was winning the NFL competition, because the data was quite similar to the data available there. In the end, it boils down to each individual player position and speed, as well as pairwise relative locations of team members and the opponents, as well as relative speeds and so forth. To simplify the structure and understanding of what exactly we're adding to the network and how we're generating features, we split it into several blocks of inputs. So the first block was about the active player, the one we're in control, things like where the player is, what is the speed, what are the current sticky actions, and so forth. Another block is the opponent, so a vector of size of 11, basically, for each opponent. What is the relative location of that opponent, relative speed, and so forth. The same with teammates, a shorter vector of 10, so where our teammates are located. The opponent's block was supposed to recognize how far the opponents are, whether the current agent should perform any actions to avoid getting tackled and so forth, and pick the proper time of shooting. With regards to the teammates block, we're hoping for the agent to learn the relative positions of the teammates to get the proper passing direction and proper timing to perform the pass. Next block is player pairs. So for each of a teammate, we also would like to look at how open the teammate is to receive a pass, meaning where are the opponents around him, how close they are, what is the direction of their movement, so how far they can block the teammate or reach him. So we construct all possible pairs of teammates versus opponents and their relative positions and speeds to basically add this information to the model. And a few other blocks which are more general, like game data. So game mode, is it a penalty, is it a free kick, is it a throw-in, ball location, speed, and so forth. We also added some historical features. So for instance, if the agent decided to shoot, it might take up to several, I think 10, maybe 20, probably around up to 10 steps to actually perform the shooting. So it was helpful for the agent to learn that shooting was chosen before. Main opponent. As soon as we didn't know which player is being controlled by the opponent agent, so we picked the closest one to the ball out of the opponent team, and also looked at exactly what is the location, the speed, and the direction of the movement. That, I believe, worked nicely for the cases where we did not have the possession, so it was quite clear which player is controlled by the opponent. Also did some offside flags for each player as well, so whether they're currently in the offside or not. And for the value function separately, we also added the active opponent. So we kind of peeked at what player is our opponent is controlling at the moment, and use that information instead of guessing by the distance to the ball. But we use it only for the value function because we don't have this information available for acting. Now moving on to the way we put it together. Yeah, this slide has a lot of arrows, but in the end, it's quite straightforward because that was a neural network which used linear layers, convolutions, and activations. So we didn't do any LSTM, we didn't do any fancy neural network structures. The only trick here is that we pulled together the blocks which are relative to the teammates. So their locations towards the locations of the opponents relative to the teammates and so forth, and the offside flags. We first pull it together to create one block relative to which describes the teammates. And then we have 6 blocks. So the active player, the opponent's block, the teammates block, game data, historical feature, and the main opponent. And then we just pull it together through a linear layer with some activations, and we get either to 19 actions probabilities, or for the critic network, which shared almost exactly the same structure, but the head, we have one output there for the value function. So it might look a little bit complicated, but in the end, it's just several blocks of data combined together through linear layers without any complicated structure. I think we tried a little bit of that, but that adds a little bit of complexity of the calculations. So acting becomes slower, and this was the bottleneck. So we decided to stick to simpler network structure to compensate for that. I believe we also tried a network which was close or hopefully identical to the one you were using in the paper, where the whole approach was a little bit different, and the players were combined into the zones, and there were zone-specific data, but it performed to our assessment worse than this structure. We also saw that some of the competitors which described their solutions also relied on similar ideas when they constructed their models. Moving on to the engineering setup, an important question for us was to properly assess the agent. So we can come up with an agent, but we don't know whether that was an improvement. If it was, what was the main direction of the improvement? What Kaggle has as an option is the ability just to submit the agent and see how it plays, but it takes a while to catch up to the proper rating level, play with proper opponents. There's a lot of variance in the game, so even if you have a stronger agent, sometimes it can lose to a weaker opponent, and the feedback is quite slow. So basically what we had in mind is that the proper rating would be there on the leaderboard probably within like a week period of time, which is definitely not a good option for us to quickly proceed with the developments. So what we did, we had kind of an internal leaderboard. So we had a pool of agents which we created via trying different ideas and by different approaches, and we just played lots of games in between them to create our own leaderboard. And whenever we create a new one or improve an existing agent, we just check the internal leaderboard, see if that was indeed the case against all the opponents. We check what was the worst opponent to the new agent as well, to specifically see if the new one just exploits some of the older ones, but still there is a strong policy out there which it didn't learn to beat and so forth. So to do that, we were relying heavily on our internal assessment. Technical setup, probably I would not go too much into details, but that was a very important thing for us because the learnings were quite slow, even though that what we stated in the beginning, 1 to 3 days to feed an agent, is quite a fast thing to get in the end. We had lots of ideas to iterate through. So we had not only to optimize the run times, but also to optimize the resources we had. Particularly, we were focusing on having a single machine to on the setup where we have a single machine to do both acting and learning, and therefore we had a setup where we store where we split the resources into the actor and learner. So learner uses GPU and some of the CPU cores. Actors utilize efficiently and actively only CPU cores and so forth. And we had a couple of machines just to keep the progress and to keep the experiments going. So we had it distributed across multiple machines, and then we collected together all the experiments running on them to see what was the progress, and then to run the internal leaderboard to assess the progress. Let's jump to the videos. Let's look at the two of them, and later we'll discuss what is the difference. These are two kind of different strategies or approaches the agents in our pool took. So there were two clusters. The first one was what I was calling exploiting this part of the environment. So if you receive the ball somewhere in the wing, you can run and then make a cross. And just because the defenders are not actually covering one of the players on the other side of the pitch, you usually score. And this is the other exploit. If you manage to run in between two defenders, you can score a goal. So here you can see we scored 2 goals within 10 minutes using these tricks which the agent learned. Let's jump to another video, and in the next video we have an agent from the other family, which does not really exploit these things, but it focuses on short passing and tries to find a teammate which is open to pass the ball to him and then to score from the box. You can see that the yellow, we score a goal here. You can see that it's not attempting to deliver the ball to the wing any longer, but it tries to keep it close to the box and just pass around. These two strategies basically came from cloning the opponents because there were two really strong teams out there on the leaderboard, and we closely monitored what they're doing and why they're successful. And we saw that these are actually two strategies that they took quite early in the competition, and they were successful for different reasons. We try to clone it and to improve on top of what we managed to learn from the replays, as well as to keep them, both of them, in the pool and create some agents which will be successful against both strategies. We ended up close to the top teams. Can you open the slide with the ranking? We ended up third, relatively close to the second team. So basically, the top team was the one who used a lot of crosses, and the second team, the one who used a lot of short passes. And I think our most successful agent was the one which started its learning from the second team. So we get close to our teachers, if you can say so. After the competition ended, we actually realized that our approach was quite a good idea, because exactly these two teams had a very heavy hardware setup, which we could not match. The first team used 800 CPU cores to do acting. The second one had, at peak times, 2,500 CPU cores. So they were running thousands of games in parallel, while our setup was, well, quite modest compared to what resources they had. We had like 30 to 100 CPU cores. So we had a couple of machines with a couple of GPUs. And also we learned that the first and second place teams, they started exploring this environment before the competition started. So they had a little bit more time to adjust and try things out. So we ended up learning from them and trying to build on top of what we learned with as much as we could do within the timeline we had and the hardware setup we had. This is it. We have another 20 minutes. I hope you have questions. Please ask anything you're interested in.
Fantastic, really good. And can I just say, the presentation, your delivery, and your explanation was top, right? The approaches you've taken, irrelevant of the approach you've taken, the way you've described what you did and why you did it is brilliant. And that, obviously that's when I think from the practical viewpoints about kind of grander implementations of whatever it is we're trying to do, and for it to have a real impact, it needs to be able to be communicatable. And I think you've done that in a really good way. So I was really impressed. So thank you very much and for our benefit too, right? You guys are extremely smart guys. And I think you've just explained it in a way that we really understand. Certainly I do. The one I would say is like one of the benefits, I think, of your approach, you talked about not trying to overcomplicate things, right? Whether that was with the hardware, whether that was with the neural networks as well. I think that's really valuable, right? If you're going to start to add in more and more complexities, you need to have kind of almost an exponential gain in the impact and the outcomes. So I felt that it's a really strong approach that you've taken in terms of trying to keep things simple where possible, right? Or when I say simple, simpler, let's say, is probably a better way of using it. So that was great. The monitoring of the other entrants as well. I think it clearly shows that one, you cared, right? You wanted to win, obviously, right? That's part of you're doing it for fun, but at the same time, you also want to win. But I love the fact that you not only monitored what others were doing, you learned from them and understood kind of what they were doing, what approaches they were taking, how you could potentially benefit from their ideas, or benefit from knowing what they are doing, let's say. So I was really impressed with that. One thing you talked about, obviously, the kind of the features that you looked into where the opposition players were, all the teammates, the pairwise approach, the space. Did you, and I might have just missed this, did you include anything like interception lines in it? So if you think about, you talked about the speed and the acceleration of players, you talked about the space. One thing that when we've looked at kind of similar approaches before, but we've never actually managed to implement, is actually the fact that a player may well be in space and may be in a vast amount of space, but maybe a long way away from the ball, whilst there may not be an opposing player who could directly block that player in terms of being right close to him or not giving him much space. He could intercept the pass depending on the kind of the trajectory and the pace of the actual pass. Is that something you looked into at all or not? If not, why not? None of it's you should have done it. It's more of just an interest as to why you did or didn't do things.
Mm-hmm. Oh, first of all, thank you very much for kind words. We do appreciate that. Yeah, we did a lot of monitoring of the opponents. That was definitely crucial because these are the teams we're going to be playing against. With regards to the setup, we did not explicitly do any analysis of what was kind of a line between the current player and the teammate, and whether there's what are the distances to the opponents for the potential of interception. I think we tried some angles-based features, which kind of do that as well, but we ended up with a simpler setup where the neural network has all the information to figure it out on its own. So we center the coordinates at the active player, and we provide all the coordinates, so all the vectors of the opponents and all the vectors of the teammates. We did that as the very first benchmark, and we challenged it a little bit, but then we saw that nothing improves that. It was an educated decision because that's the structure of the network which was used for the NFL competition to win. I'm mentioning it a few times because it correlates a lot, because the structure of the data is exactly the same. So what they had is coordinates of the players and the speeds, so all the vectors. And during that competition, a lot of different structures were tried out. And as soon as it was not reinforcement learning, but a supervised learning competition, the stress was exactly on the architecture. So a lot of approaches were tested, and exactly the more simple one was the most efficient and the most successful in terms of the accuracy of the final prediction. And the logic was exactly like this. So as soon as we know all the coordinates, we can not only deduct all the angles or the distances, but also some probabilistic things from the relative locations of the players. And with sufficient number of training data points and sufficient size of the network, we knew it can learn as much as needed from the relative locations.
Cool. Yeah, so to summarize, I would say it's conceptually simpler, but it's also a general architecture. So I think, yeah, implicitly we are monitoring interception lines with this architecture.
Yeah, that makes sense. So I'm gonna ask one more question. I'm gonna leave it because obviously we'll have a follow-up call, which I'd like to do with you guys and with the wider team for you to kind of question us as well, right? But no doubt we'll probably just have a really cool conversation, right? Just not just about your work, not just about ours, but just about the application of these sorts of models to football and how they can impact, or to any sport ultimately. But I have got one more question before I kind of hand over to anyone else who might have any, which is, what would you like to do if we said, right, go at it again now? What would you do different, if anything? But more importantly, what would be your future aspirations with this if you decide, I'd love to kind of crack on with this? I feel like you've got it all prepared.
Of course, yeah. I think Tom has, yeah, there's a good slide for that. We have certain things about the environment and certain things about the topic, but Tom, please go on.
Yeah, so I think it was an amazing competition. It was already very challenging as it is, but it's not good enough to get real football insights. So I think, yeah, the problem is that it's a simulation, and it's very hard to get a realistic simulation. And especially problematic, we think, was the naive built-in AI. So we only controlled one player, right? So this competition was really about exploiting the naivety of the non-controlled players. There was also like an issue with the referee, a real issue, in the sense that sometimes you got away with crazy tackles. Sometimes you would strategically tackle an opponent to get an advantage. And I think addressing these two would be key focus areas to make it more realistic and therefore more useful for actual football implications.
I love. Yeah, sorry, I agree. I get you. I love, though, how realistic you've made it in your mind, in the sense of you're blaming the referee, just like football players and managers do across the world every single week. I think that
yes,
there must be some realism in that. No, but yeah, I agree. I think one of my questions would be to you, and this is quite a broad one, right? Is given the somewhat chaotic nature of football, right? We might know what teams and players want to do and try to do or are set out to do, but don't necessarily do it, and that's because they're humans, right? How possible do you think it is to create I'm going to say a realistic simulator? What I mean is a simulator that is good enough. It's close enough to being realistic. How would you, if I pose that question to you, do you think that's achievable at some point in the future? What would your kind of gut and your brains tell you?
I think like the real insights, they're not necessarily going to come from a simulator. Like you would have to model all human psychology, and you would have to model the weather and like the effect of the wife at home and the kids. Like everything would have to go into this model. I don't think that can be achieved. I think it's a good simulator, and I think there's more to be gained from these types of ideas rather than just from the simulator. And I think, yeah, our core suggestion, I think Dmitry can elaborate on that, would be to use some sort of a value function to assess how good the current state is. Like, given the current observation, how good is this for the team that we care about? And then you could use the evolution of that value function to assign credit for individual actions. So that way we would no longer care about things like assists and goals, but we would care about all micro actions on the pitch. And that way you could assign credit to every single micro action of all the players. Think of it as expected goals, but taken to the extreme, where you use learned stats to assign credit to the actions of all players.
That's beautifully put. One of the reasons I say that is we took in one of our like early day kind of rough simulator projects we ran over a course of a summer, I think it was, with a local university close to us. That's what we gave them, right? We gave them a value around pitch control. I don't know. By the sounds of it, you obviously have done a bit of research into space, or know space a little bit in terms of football analytics. We looked into pitch control. We used that as kind of the target variable for our kind of bots. And the idea being, the goal would be, is can we identify the actions that increase your team's pitch control or decreases the opposition team's pitch control? Now, they could be actions of a unit, such as defensive line and the stability of the defensive line, or they could be individuals' movements, such as runs in behind or dropping into space, etc. So I really like that, and we should definitely pick this up in the next conversation in more detail.
Tom,
Yeah,
I have a quick question for you, Tom. What would you need to change in your approach to go multi-agent?
We need to get more hardware, I guess.
But also conceptually, like
conceptually, I think
if you go multi-agent, you really want your agents to collaborate, right? So you want to use a central brain. And one thing you could do is, rather than selecting one action, you select all actions of all the players. Like, you want to learn to coordinate your actions. So conceptually, it would not be a huge change.
It's an interesting thought. I need to think a bit more about the concept of a central brain for autonomous agents to get them to collaborate. It's an interesting concept, but thank you.
Well, I did a lot of research into control of human body, and there you had to control all the joints at the same time. Think of the players as the different joints in this setup. So you would just use the same RL setup, but you jointly try to optimize all the players. But we would definitely have to change the referee, because if you tackle away from the ball, you get away with that. So you can use all aggressions to get space.
So it's good for the NFL model, right? You can run all sorts of tackle blockers.
I mean, I think I won't repeat what's been said about. Well, I will repeat very briefly what's been said about how impressive your submission and presentation was. I think the thing that stands out for me actually from the presentation is that actually, as imperfect as this is, the sort of core, I think you talked about 3 core, what I would describe as football insights that were generated. One being getting the ball out wide and essentially creating an overload on one side so that a player frees up on the other side is an effective strategy. The second is that close, tight control in and around the box, close, tight passing in and around the box is an effective strategy. And the third being, sort of effectively a line break, between 2 centrally placed defenders is an effective strategy. I mean, they are core football insights that I think would be recognisable to any modern coaching team. So as imperfect as the environment and the learning is, I think, you can already see it. It didn't come up with insights that you would immediately discount as being useless.
Well, you didn't see our first couple of agents. They were like 5-year-olds running around on the pitch, just never passing, running straight at the goal.
Well, and they learned not to do that, right? So there you go. I saw. I know we've only got a few minutes left. I saw you had a couple of questions for us, Tom and Dmitry, on things like the visit to Manchester. So I'm just keen to make sure that we address those. Probably the most straightforward from our point of view is this question of the trip to Manchester, and I think Brian, jump in here, but I think to some extent this is obviously very difficult to answer in the current situation. I think what we thought was, let's get going virtually. So in our head we were going to set up a longer meeting. I don't know exactly how long yet, but certainly with a bit more space and time than this one, with a few more people from our side, more like a sort of open workshop to perhaps start from this material, but have a far more open and wide-ranging conversation about the work that we're doing, the work that you're doing, and how these things might tie together. So that, we don't necessarily rule out a trip to Manchester in the future, but we certainly would recommend, particularly given that we've got no visibility on when that might happen, that we start in a more virtual way. I can see you both nodding that that's kind of okay. But Brian, do you want to add anything?
No, I agree. I mean, I think that's the right approach, and I think we should kind of get that in place as soon as possible and kind of get that virtual session up and running, and then we can kind of evolve from there. It's obviously it would be much better to have had you guys in person, which still could hopefully will be possible in the future at some point, who knows when. But yeah, I'd echo what Greg said. Let's get started virtually and work from there. The other points, Greg, do you want to jump in or do you want me to?
Well, I think we've sort of covered the first two certainly the second one. I mean, I think you've covered it a little bit, Brian. We have a long-term strategic aim to be able to genuinely use this sort of technology to assist our coaching and our planning for real games. You said more about it earlier, but I think that I hope it's clear that we're very, very interested in this whole area. We do believe in its potential, as a sort of adjunct and an aid to the more traditional coaching methods that have been used for a long time. I think the question on the follow-up competition is perhaps more one for Addison and Petter.
So from brain perspective, we are all in. And we had discussions about multi-agent competition where you can control all the players on the team. So we're interested what contestants can come up with there.
Yeah, like one cool concept would be that you're paired with a random opponent, which then is your teammate, and you all control one player, and then you have to figure out how to collaborate.
Mm-hmm.
Yeah, and on our end, just to give you a heads up, we're excited about it. We're trying to work on some hardware stuff. We also recognize the load on the infrastructure, so we're trying to figure that out.
And I know from our side, we would definitely love to see that, but we're pretty much in the hands of your technical expertise at Kaggle and Google. So.
So one question I wanted to ask is, what was this cost split in terms of compute resources and different components that you had, like environment, training, inference? What was the most expensive one, for instance?
So yeah, go ahead, Dmitry. I have
Oh yeah, go ahead. I don't have any numbers in my mind.
Like I did some profiling, and about half the time is spent in the environment interaction, half the time in all our logic around it on the actor side. And in terms of learning, of course, we don't do environment interactions there, which was the other half. So maybe a quarter of resources is spent in the actual environment. But it's definitely the bottleneck. So yeah, I know Dmitry has some ideas on how to improve that bottleneck.
All right.
Yeah, I have one idea which I would be happy to share how we can like optimize that part, but yeah, we can discuss it any time you're available.
Sure, that I'm open for discussion. I can follow up over email and we can schedule something. Thanks.
Okay, that's great. I mean, the biggest thing from my end now is obviously we'll set up a follow-up call to do this. We'll send out an email, Dmitry, Tom, just for you, and we can kind of sort out the availability, the schedule, when to do this, and we'll invite kind of some of the wider team that will be relevant to the call, and you may be interest to you. I guess one question to you guys is there anything you would like, if you were coming to Manchester and we were doing it in person in say 3-4 weeks time, what would you like to have achieved out of that for you guys? It'll help us understand kind of maybe if there's anyone else we need to bring on the call that we weren't planning to, or what we might want to cover.
I think it would be really exciting to add value to Manchester City. Like, if you could scope down what you think are interesting areas you want to solve analytically to us, that could be a good place to start.
Cool.
Absolutely. So bringing value to any decision making, whether it's scouting or managing the team, this would be the best possible achievement. But I can imagine how difficult it is, because probably mindset of scouts and managers is not that much focused on analytics and simulations.
Yeah. So yes, absolutely. By the way, great. You framed it exactly how I would frame it, which perhaps I don't know whether it's always good to have people who just think the same, but I love the fact that you said that. It sounds like the right approach, right? You think about the decisions, the big impact areas, and you focus on them, and let's work with those. One thing I would say, Dmitry, is you'll be surprised actually across City Football Group. I've worked across many clubs, and it's a little bit different. The mindset of the coach. There's a reason why the coaches we have are some of the best in the world, in particular at Manchester, because they do have that very kind of open growth mindset, and they like to learn, and they might not always understand, but they like to learn and they like to know, and they like information that has an impact, right? So if anyone can create an impact, that's what really matters. I'm conscious of time now, so we best kind of probably jump off. I'll send a follow-up email, Dmitry and Tom, to set up that time. Addison, Peter, obviously fantastic as always. So thank you very much for kind of setting this up and hosting, etc. So I just want to say thank you. That was all.
Yeah.
Thanks a lot, guys. That was really fun.
That's right.
Yeah, thanks a lot, and hear from you soon.
Tom and Dmitry, you are one of our first calls, so we have the other 2 winners calls. Once those have finalized, we'll release some of the prize money your way, and as has been discussed, we'll also work through We'll let the Manchester team work through the trip, as well as sort of any upcoming additional presentations. But congratulations again.
Absolutely.
Thanks,
Thanks
guys.
a lot.
Great work, guys.
Take care.
Bye.
Bye.
Take care.